Hi, everybody. Today we're going to look at by far the shortest section of Calculus 2 that we're going to have, and it's the strategy for testing series. The online homework, the way that this works, is it basically just asks you to find convergence or divergence of the different series. But understand that when you're studying for the test, I'm probably not going to ask you very often to just come up with your own way of testing the series. Instead, I might ask, what is the proper technique? So this section, instead of focusing on actually finding convergence or divergence, I'm going to show you a strategy that if you don't know what to use, it's sort of the order you should look to solve these problems. All right, so let's get into it. So at this point, we have several ways of testing a series, right? I think we have 8 different tests. The problem is to decide which test to use on which series. In this respect, testing series is similar to integrating functions. And you remember Chapter 7, Techniques of Integration, where you had to just pick a technique and see what happens. So no hard and fast rules about which test to apply to a given series, but there are some guidelines you can use. It is not wise to apply a list of the tests in a specific order until one finally works. It's a waste of time and effort. So the main strategy is to classify the series. So here is a single list. This is what you should use to do the problems, the homework problems in section 11.7. Notice p-series and geometric series are not tests. And there's also another missing test. And it's more of a technique. It's more of a strategy that we saw in the ratio test. Comparison tests is actually 2 different tests, right? So I think there's sort of 7 tests and a technique. All right. Always the easiest one to do is if you notice that the sequence of the ANs are not going to 0, apply the test for divergence. If it shows that indeed AN is not 0, the limit, then it has failed the test for divergence, and the series diverges. So that's, if you're not sure, it's always the easiest thing to try. If you recognize that your series is in fact a p-series, then p greater than 1 converges, p less than or equal to 1 diverges. So it's another easy one. So any constant multiple of a p-series. Just things like that. Geometric series, very similar, right? If it's in the form sum of the AR to the n or AR to the n minus 1, converges for r less than 1, diverges for r greater than or equal to 1. So these are also the two main comparison series as we saw in Chapter 11. So if you can compare something to a p-series, use either direct comparison test or limit comparison test. Same thing with geometric series, right? Direct comparison or limit comparison test. So if the sum of the AN, so this is for comparison tests, if there are roots and polynomials contained in it, only roots and polynomials, compare it to a p-series. Geometric series look a little bit different. If AN has negative terms, test absolute value of AN for absolute convergence. This is the technique I was talking about. You can always test for absolute convergence. And if it's absolutely convergent, it's convergent. And that's also the technique we use for the alternating series test. Right? Where we might test for absolute convergence and get convergence. But the alternating series test doesn't require that, right? The alternating series test, it just has to be alternating, and the BNs go to 0. Right? The limit of the BNs. So if it's alternating and it passes the test for divergence, it converges. So the divergence test and the alternating series test go together, and testing for absolute convergence with these comparison tests also goes together with the alternating series test. Ratio test, if you see factorials and other products, right? So exponentials, factorials, other stuff like that. Use the ratio test, sines and cosines, stuff like that. But don't use this with roots and polynomials. Roots and polynomials, you want to do comparison test. Root test is the easiest one. If you see an n in an exponent, do the root test. Or n to any power in an exponent, go ahead and do the root test. Then the last one was a test we studied kind of earlier in chapter 11. But it's the last test to use because these integrals can be hard to do. So if you don't see an easy integral to do, it's probably not the integral test. So just replace the n's with x's and imagine if you can do the integral. But it's usually the last thing you try, unless you recognize the form as being something that you can integrate. So there's only one example in this section. We're just going to look at a few of these and talk about them. When you get to the homework, you are actually finding convergence and divergence. But understand that on a test for this particular section, I'm more focused on what test should you use and why, as opposed to convergence or divergence. So let's just go through them and look. All right, so what kind of series is this? Well, let's go back and look at the form. Right, we have these forms. I see roots and polynomials, right? I see polynomials. Right here. That's a polynomial, that's a polynomial. So you might be thinking P series. Or you can take the limit. Just imagine what happens if n gets really big here. Right? We went over this. So as n gets really big, the limit of this approaches 1/5. So we could try the divergence test because 1/5 is not 0. And it turns out that that's the way you should do it. Right? The limit of this is 1/5, which is not 0. So that this fails the divergence test and it diverges. So I'm not asking you to actually prove it for this particular section. Just think more about what should I use? What test would fit? All right, let's look at the next one. So this is mixed. Here we have polynomials, and here we have an exponential. So you might be thinking ratio test. Go ahead and try the ratio test. You'll find that you kind of run into a problem. So it turns out this is the integral test. If you replace the n's with x's and put an integral, this is a use substitution problem. Right? Because the derivative, if these n's are x's, the derivative of this is a constant multiple of this. So this is actually a really easy problem to do using the integral test. Whereas the integral test normally isn't your first choice. If you try the ratio test or one of the other tests, you won't be able to do it. Again, if you're not sure why, go ahead and try the ratio test on that, and you'll see why. All right, last one. We have more polynomials here, but this one's alternating. So there's lots of stuff we can use here. You can take the absolute value and show absolute convergence, but it turns out that doesn't work. If you try to show absolute convergence here, this becomes a P series with P equals 1, because n cubed divided by n to the fourth is a P series P equals 1. This would fail the absolute convergence. So this is one of those that the only thing you can really do is look at this alternating part and use the alternating series test. So remember, the alternating series test has two different parts. It has to alternate, and this term has to go to 0, which it does, right? It's the same as 1 over n, which goes to 0. But you can't just take the absolute value and show that, because the comparison test you would use is the P series, and it would not be able to show convergence. So alternating series test is the right test to use here. So this is just a quick example of the types of things that you're going to want to do on a test for this section. Like I said, I'm not going to just give you a series and say test it. If I give you a series and say test it, I will tell you what technique to use, or the technique should be clear what to use. So this one, it is not clear that this is the integral test. I would tell you to use the integral test. Or if it's this one, I would tell you to use the alternating series test if I want you to find convergence or divergence. But if I just want you to pick what test to use, it'll look something like this on a test. All right, well, really short section. Like I said, you should be able to knock out the homework if you've gotten everything done to this point. And if you have any questions, let me know. And I'll see you next video. Bye-bye.